Hi everyone, borehole samples descriptions and the results of classification tests are used to divide the soil samples into groups with expected similar engineering behavior. The parameters frequently required are the bulk unit weight, the effective strength parameters, cohesion and friction angle, the undrained shear strength of clay, the stiffness for prediction of movement, the coefficient of consolidation, the coefficient of permeability. The bulk unit weight of soil is normally expressed in kilonewton per meter cubes. It can be obtained from bulk density by multiplying it by the gravitational constant. Bulk density is expressed in milligram per meter cube. Bulk unit weight should not be confused with buoyant unit weight, which is the difference between bulk unit weight and the unit weight of water. It is recommended that the buoyant unit weight should not be used in air pressure calculation, since this can lead to confusion. When a coarse granular material is above the groundwater table, its pore space will contain air. When below the groundwater table, the pore space will be full of water. As a consequence, the bulk unit weight of soil will be higher. As you can see, these typical values. Clays will not normally have a significantly different bulk unit weight above and below the groundwater table, since capillary suction can maintain their pore spaces full of water. As we can see, these similar values. A number of different laboratory and institute tests are available for determining the peak strength of soils. Except in the case of very small structures, the strength properties of cohesive soils are normally obtained by testing good quality undisturbed samples in the laboratory. The stability of earth-retaining structures will normally be at its minimum in the long term, so that for most design in the peak effective parameters that are required for earth pressure calculations. These can be obtained as follows. For clays, consolidate the undrained terrestrial compression tests with a pore pressure measurement to find the effective cohesion and the effective friction angle on undisturbed till samples obtained from boreholes or block samples obtained from trial pits. For sand and gravels, the effective strength parameters are required for the in-situ soil, but it is not possible to obtain undisturbed samples. Generally, although the failure envelope for the soil may be curved, effective corrosion is assumed to be zero. The peak effective angle of friction is determined from the correlation with the in-situ penetration test results. The peak effective angle of friction of cohesive soil do not vary widely, but the effective cohesion intercept may be very different from one soil type to another and from one test result to another. For normally consolidated clays, the effective cohesion is equal to 0. And as soil becomes more heavily over-consolidated or boarded, its effective cohesion intercept is found to increase. Typically, the effective cohesion between 0 and 10 kilonewton per meter squares, and the effective friction angle between 18 and 30 degrees. It is unwise to assume an effective cohesion intercept for more than about 3 kilonewton per meter squares, even if the soil is heavily over-consolidated, and it may be sensible to assume effective cohesion to be 0 in most cases. In the absence of any triaxial data, The angle of friction can be estimated from the plasticity index from result by Kenny in 1959. The method described give effective strength parameters for failure in triaxial compression conditions. For clays, the difference is thought to be slight, however, so that triaxial values can be used with confidence since they will be on the safe side. Granular soil. The effective strength parameters of a granular soil are a function of particle size distribution, soil density, imposed stress level, angularity, and cementation. They could obtain from series of laboratory tests of representative disturbed samples obtained during in situ investigation and recompacted through a range of density, but in practice, the effective cohesion is assumed to be zero, and the friction angle is commonly estimated from SPT or CPT values, such as given in the figure. This is for SPT test. Note that these charts were derived from sands, and as noted above, coarser grained soils such as gravel will have an effect on penetration resistance, which may not be completely a reflection of an increased angle of friction. Alternatively, Lundgren and Breen-Hansel suggest the following methods of estimating phi prime for granular soils. Phi prime is equal to 36 plus phi 1, which is the shape, which is the correction for particle shapes, phi 2, which is the correction for particle size, phi 3, which is the correction for the grading, and phi 4, which is the correction for the relative density. Wall friction is created in the soil because of contact with the wall surface, while wall adhesion is the component of shear strength between the back of the wall and the soil it supports. The amount of mobilized wall friction and wall adhesion are a function of the strength parameter of the soils, since the shear strength between the soil and the wall cannot exceed the shear strength along a parallel plane in the soil a short distance away. The frictional properties of the back of the wall, the direction of movement of the wall with respect to the soil, the amount of relative wall-soil movement, the ability of the wall to support the vertical force implied by the wall friction and adhesion. Thus, the mobilized effective angle of wall friction, delta prime, must be less than the effective angle of friction of subsoil, and the effective wall adhesion must be less than the effective soil that is assumed. Values of undrained shear strength may be required for determination of earth pressure exerted by clays under undrained conditions, the calculation of earth pressure exerted by clays on braced excavation, the determination of bearing capacity, for example, for clay supporting the foundation of gravity walls, and for reinforcement earth. The undrained shear strength of a saturated soil will normally be determined by an unconsolidated undrained triaxial test where the specimen is compressed at a constant rate of strain and failure in about 10 minutes. Other methods of obtaining the undrained shear strength of cohesive soils are the in situ vein test for soft and saturated soil, the plate bearing test, via correlation of SPT values, via correlation with static cone resistance. it should be noted that undrained shear strength is dependent on test techniques, and different values will therefore result from each type of test in the same soil. In the absence of test data and for small structures, only an approximate value of undrained shear strength can be obtained from records. For small walls, where a design can be over-conservative without unacceptable financial penalty, it is acceptable to use the result of odometer testing to determine a value of Young modulus of clay, for example, to determine the settlement of a gravity wall. Strictly and ignoring bedding, the constrained effective modulus E'(C) is obtained from the coefficient of compressibility determined from an odometer test. In stiff clays, bedding between the apparatus and the specimen has a significant effect on measured strains, reducing the modulus obtained by up to an order of magnitude, so that any settlement will be overestimated. In soft clays, the value obtained will be more reasonable. The stiffness of granular soil will normally be determined from result of penetrating tests. Back analysis of Berland and Burbridge data suggests the relationship between the Young modulus and the number of blows of SPT test for immediate settlement given in the table. Stiffness can also be estimated from CPT test. Correlations between effective constrained modulus have been expressed in the following, where the value of alpha m is often stated to be range between 1/2 and 4. Thank you. Click on like if you have been liking the video. Don't forget to subscribe to be notified when the next video will be available. Let's see the next time.